Okay, I think we had a couple of lectures before for the digital electronics section. There we covered several topics of digital electronics part. Okay, then from today onwards, that we have to spend another set of hours uh, to study about the basic concepts of analog electronics. It's totally different from what we have learned from the previous one, the digital electronics section. But actually, that this analog electronics section, from doing this one, that you can learn the fundamentals, basics of the analog electronics. Okay, but you have learned all the fundamentals and basics of the digital electronics. Then you have some kind of idea after finishing completing this module also. Then you will have some kind of understanding, the design ideas, and the problem solving ability completing these two modules. Okay. Anyway, that we are very much behind the schedule without having much more introductions and whatever the thing that we can straight away go to the subject matters. But anyway, that saying like that, it doesn't mean that you can ask questions, you can't ask questions, and we cannot spend much more time for the understanding of the topics. Whatever the problem that you are having, you feel free to ask any questions, and if you bring many questions, that everyone can learn all these things. Okay, that from analog electronics section, actually we are going to discuss about basically the component. When you consider the components, I think you may remember under the circuit theory section, we have discussed about the passive components, resistors, and we didn't cover capacitors and inductors, but anyway, the resistors and other diodes and other networks we discussed. Okay, but we didn't discuss the diode applications, the transistor applications, and op-amp applications. We didn't discuss there because our primary concern, primary aim was there is to learn about the circuit theories. And when we connect couple of components together, the passive components together, then how these voltages get divided that across the devices, and maybe how the currents are going on through the branches like that. Those are the things we have discussed there. But in this section, we are going to cover the applications and the basic understanding of diodes, transistors, and operational amplifiers. Okay, those are the three components, maybe modules, and we are going to cover up under this section. Okay, here we are going to discuss about theories behind this, how these devices are formed, and how these devices are operating under different conditions. And those are the things we're going to discuss. Okay, first of all, that before we start anything, we should know, I think some of you may already know about these things, but some of you not aware of these things. Because of that, we can start from the beginning. Then it doesn't matter that anyone can start anyone can understand all these things, because we are starting from the beginning. Okay. The first important thing here, we have to study about PN junction. Okay. Before we start PN junction, before we start to study about PN junction, first we have to understand the behavior of semiconductors. Semiconductors. You know about conductors. You know, because you are doing the related subject well, then because of that, you have some kind of idea about the basic elements of the periodic table, and you know that what type of elements are conductors and what type of elements are insulators, and why they are insulators and why they are conductors. And I think you know about all these things. Because of that, I am not going to discuss about this. But what about semiconductors? Why do we have this name semiconductor? Because it's having kind of conducting characteristics. At the same time, it's having some kind of insulator side characteristics also. Okay, and basically that we are when we consider the fourth elements of periodic table. First, we discuss about the fourth element, silicon, germanium. These two elements are the most popular elements to make semiconductors. Okay, I think without having much more discussions, I think you know about all these things, that the silicon is having 4 electrons in the outer circle. Then because of that, I think for the stability, it needs another 4 electrons. But here that it doesn't have that one. Because of that, it's sharing another 4 electrons with neighbor atoms. Okay, then it can have this type of bonds between that neighboring atoms. Okay, like that you can see some kind of that the structure is there. But after making these bonds here, that you know that there is no free electrons for the conduction of for the electricity. Because of that, we can say in this stage, if the silicon is in this stage, we can say this is a insulator. It shows that insulation characteristics. Why? There is no free electrons for the conduction. But you know that these bonds are not very strong bonds, and when the temperature increases, and some of these bonds may be broken. Okay, then because of this that broken bonds, then some of the electrons maybe get freed. Example, if you take this one. Assume that here, because of the temperature increases, this bond breaks, that these electrons comes to the out of the structure, and after that, here we have vacancy here. Okay, then after then we have, you know, that this is electron. We have electrons here, that's a negative charge, and because of that, this electron has moved out. Then here we have positive charge. Yes, this is negative charge, and we say this one is a hole. Okay, and it's positive charge is there. Okay, and this is the way that we can see that when the temperature increases, and how these free electrons are coming into the lattice. Then like that, the different atoms may release some electrons to the structure. Then couple of free electrons may be available because of this temperature increases. Okay, then at the same time, you can see here the number of electrons. Number of electrons here, it's equals to number of holes. Okay, if you have such situation, because that here we don't have anything other than these 3 electrons, then throughout this structure, throughout this lattice, now electrons can move. Electrons can move means the electricity we can send electricity through this structure. Okay, then now it's showing some kind of conducting characteristics, but not whole, not like all other metals like conductors, but this shows partial conducting characteristics. Because of that, we say these are semiconductors. Okay, these are semiconductors. But in these semiconductors, number of electrons and number of holes, they are equal. And if we have such situation, we say these are intrinsic semiconductors. Okay, intrinsic semiconductors. Then with this intrinsic semiconductors, you know that you can understand conductivity. The conductivity will be increased when the temperature increases. Okay, but you know that this is the fourth element, fourth group element, the silicon, and the same thing here. If we take germanium also, germanium also having the same structure like this, and the same situation. From germanium also we can expect from this intrinsic semiconductor characteristics. Okay, but after that, then especially that you can see now we have this structure here. Silicon, here, silicon. When we have this structure, and what we are going to do is that actually what people after realizing all these things, and what they have done is that they have introduced some kind of different elements into this structure. For example, we can take third group element, it's a boron. After taking that, you know that after taking this boron into this structure, you know that here all these are having 4 electrons in the outer circle. And they are having bonds like this. Okay. But in this boron, you know that only 3 electrons are available in the outer circle. And because of that, it can make bonds like this. Here, we don't have anything. Because of that, here we have a hole. And here we don't have any bond. With this, all these other electrons are having this type of bonds. But we introduce this impurity element here. And what will happen after introducing this? That before we introduce this one, we have this silicon structure, and here then electrons maybe has come to the structure, and here we have one hole, and here also. And this is a normal situation. But while we are having this type of thing, and we introduce a new element to this one, this third group element, because of this introduction, we have one extra hole here. When you consider this one, the before this one, that number of electrons equals to number of holes. Now, because of this introduction, then after adding this one, after adding this boron here, now what will happen? The number of electrons are less than the total number of holes. Why? Here we have introduced some other holes because of this third group element. Okay. Then when you consider the whole structure, what type of characteristics we can see? The previously we have the number of electrons equal to number of holes. Now in this structure, number of holes are more than number of electrons. Because of that, in this set, we have positive characteristics. Okay. Then it shows some kind of positive characteristics. Okay. Then when you have this type of arrangement, then we see this is positive type semiconductor. Why? We have more holes here, and then we say this is p-type semiconductor. Okay. And when we have this type of criteria here, then these type of semiconductors are, we say they are extrinsic semiconductors. Okay. Like this, then we can make this p-type semiconductor. Now adding this one and making this p-type semiconductor, what we have done basically, we have increased the conductivity. How? Because the number of holes are increased. Anyway, that number of holes are increased with the electrons can move to that location, that the different electron can move to the next one, and the hole can be moved, or maybe you can say the electrons can be moved like that. These free carriers, then we can say this actually we say these are the number of electrons. The electrons are the negative carriers, and holes are the positive carriers. Whatever the carriers, the negative carriers or positive carriers, that they can move across the structure. Okay, when that this bond can be come here, and then actually this hole can move to this location, then these electrons can come here. Like that, holes also we can consider. Holes also can be moved, and the electrons also is freely available. Anyway, it can move. Okay. This is the story behind this p-type semiconductors. Okay, then you can take this one copied. Okay, now here we have introduced third group element. But what about if you introduce element from fifth group, then if you do that one, like sulfur, then here it's having 5 electrons in the outer circle. Now it can make bonds like this, but anyway, 1 electron is the additional electron is there. Then because of that, if you do like this, sorry, sulfur is, it should be, you can say phosphorus. Yes. Then with this phosphorus induction, then we are having 1 free electron more. But before we introduce this one, the fifth element one, after adding phosphorus here, now what will happen? This number of electrons increase, then number of holes. But one thing you have to remember that introducing this new material here, the impurity material here, that we can increase one type of free carriers, but does it mean that other type of carriers are not available there? No, both carriers are available, but one major carrier may be there. The major carriers may be electrons in this type of structure, and the previous one here, in this case, the majority carriers are holes, and minority carriers are also there. Before we introduce this third group or fifth group element, the silicon structure is there. It's having both electrons and holes are equal. The number of electrons and number of holes are equal. Because of that, they are intrinsic semiconductors. In the intrinsic semiconductors, both carriers are having equal numbers. Then there we don't have majority carriers or minority carriers. But after introducing this type of element, maybe from third group or fifth group, now we have the concept of majority carriers and minority carriers. In this one, the p-type semiconductors, majority carriers are holes and minority carriers are still there. They are electrons. In here, this number of electrons here, they are greater than the number of holes. Then we say these are negative type. Negative type semiconductors. Why? The negative characteristics are here. Okay, then this is n-type semiconductors. Okay. They are negative type semiconductors. And these are majority carriers and they are minority carriers. And here, these are minority and they are majority. Is it okay? Okay, if you're okay with this one, now we have this type of and if we say this is P type, you know that majority carriers are false. Then here we have positive type charges. And if this is N-type semiconductor, negative type semiconductor, and majority carriers are electrons. Here we have holes and electrons. Now we are going to discuss, and when we join these two parts together, and we have PN junction, and after that, what will happen? That's what we want to discuss. Okay. Considering this situation here, okay, we can bring these two pieces together and try to understand what will happen after that. Okay. Assume that this is the barrier here, this is the junction here, and here and this is the situation, and when we connect these two types together, okay. But what will happen after that? Because of this junction, the nearby carriers, nearby majority carriers can go to the other side and get neutralized. Because the attraction is there, this positive negative attraction is there. Because of this attraction, okay, this can go to this side and get neutralized. Okay. After connecting this one, you can move across this junction and go to the other side and get neutralized. Then after that, here we don't have these charges anymore. Then some kind of region has been created, and within this region, majority carriers are not there. But you know that still minority carriers are. And what are the minority carriers of this region? What are the minority carriers of this region? Electrons. Okay. Some electrons may be there, some the holes may be there. Because of that, it creates a potential barrier like this. Actually, some kind of voltage across this one. This is positive to the it creates a kind of battery, but we don't think like that it's a battery. But it creates some kind of the voltage region, the potential here because of this minority carriers. Okay. But here, then this attraction is here. Then because of that, no more charges, no more majority carriers go to the other side to get neutralized. Why? the near the junction. Now this minority carriers are the prominent carriers. Okay, here because of that. Okay, forget about that one after that. Okay, in the simple terms, to explain this one in different way, we can forget about these things and think like that. Okay. Then sometimes that this is happen, after moving this one, after copying this one, the okay, now it's okay. Here we can delete. In this block, we can't do that. These type of things cannot be explained, but it is happening. Okay. Now you can see that near this junction, and we have created this type of region. Actually, we call this region is depletion layer. This is this depletion layer. And because of this depletion layer, these majority carriers from one side to other side, the movement is stopped. And they can't move across this junction, but nearby majority carriers can go to the other side and get utilized. But after that, after doing that one, uh, the far away majority carriers, they can't move to the other side because of this depletion layer. Okay, this is the PN junction story. And up to this point, then do you have any question before we discuss? Anything? Any question? Okay, if you have any question, that let me know. Then I can ask the question. Then okay, assuming that you have understood all these things, and we can go beyond that. Okay, now what we are going to do is that we are going to apply certain voltage across this one, because you know that P type is semiconductor and N type material is this one is also semiconductor. Now what we have done here is that we have combined these two things to make PN junction. Now we have different device. It's a device. And with this device, what we are going to do is that we are going to apply that as normal way. We are going to apply some voltages and currents here. And we are going to check what will happen after that. Okay. But you know that in the normal setup, the conduction is not possible across this the junction. Why? We have this depletion layer. While we are having this one, we are trying to apply voltages here. Shall we check that what will happen after that? Okay, here. Now what we are going to do is that we are going to apply a voltage. And assume that this voltage can be varied. here we have certain voltage, and this voltage can be varied. We can take it from 0 to some other high voltage one. And this is the positive side of the battery, and this is the negative side of the battery. And because of that, this positiveness has come here. And here we have the positive charges collected at this terminal. And here also you can see the negative charges has come here, and negativeness of this battery has come to this side also. Now at this terminal is negative. This terminal is positive. Because of this one. Now here negative, negative. This charges majority carriers are also negative, and from the battery also this side is negative. And from this side, from the battery, this side terminal is positive, and the majority carriers here is also positive. Because of that, okay, then what will happen after that? Okay, what will happen? Because of these positive charges, because of this positiveness of this one, these positive charges, these majority carriers will be repelled from this terminal towards the center of the device, towards the junction. These positive charges will be repelled. And this here we are building up a certain force. Certain force has been built up to send these majority carriers away from the terminal, and they are going towards the junction. Okay, is it okay? Then with this arrangement, this is P and N, we can increase this voltage more. Okay, we can increase this voltage more, and because of this arrangement, you know that in the previous case, that these majority carriers have been moved towards the junction, and this side also electrons are coming towards junction, and because of that, they are coming towards this one. Because of that, here this depletion layer with this decrease. So these ones has come towards the junction, and because of that, the depletion width of this depletion layer has been decreased. Okay, then we can increase this voltage more. Then we can increase this voltage more. Then when we increase this voltage more, what will happen? The more positive charges will be collected at the term, and it pushes these majority carriers more towards the junction, and it creates much more force on these majority carriers, and because of that force, they are moving towards the junction, and as a result, what will happen? As a result, what will happen? The width of this depletion layer is decreasing. Is it okay? Any question? This one? Any question regarding this one? We can copy this one. And as a result, you can see now we have increased this voltage more, like this. This is positive, negative, and we have increased this voltage more. And because of that, more positive charges have been connected. And then as a result, this depletion layer, the previous case, the width of this depletion layer has been decreased. And here we can assume that as a result, this depletion layer is almost here, and there is no barrier, and the layer width may be the 0, and these charges come here, and because of that, they can cross the barrier, they can cross the border, and they can go to the other side. Okay. After increasing this voltage to a certain level, you know that this terminal, the more positiveness is there, here more negativeness is there. Because of that, they are repelling these majority carriers towards the junction. Then after creating this force a little bit more, then these majority carriers are very much close to the junction. Then because of that, the depletion layer has been decreased, it's almost 0. Then these majority carriers can cross the border. Crossing the border means what will happen in external path. Here we can see, as a result, in this path, we can see there is a current going through the junction. Okay, there's a current going through the junction. And when we have this mode, we say that what we have done here and what we have done here. Okay, then what we have done, that we have connected a battery. This is positive terminal of the PN junction. This is negative terminal of the PN junction. And we have connected negative side to the bell. Negative terminal, in terminal, and we have connected the positive side of the battery to the P terminal. Then if we have connected, and if when we increase certain voltage, then after increasing that voltage, then depletion layer will be broken, and after that the majority carriers can go to the other side. Then as a result, in the external part, we can see the current is going. Okay, then we say this mode is forward bias mode. And in simple words, when we forward bias the PN junction, we can see the current is there. Current can go through the device. Okay, but anyway, when you know that when we have the small voltage, that small voltage cannot break this depletion layer. We need more voltage, and we have to increase the voltage a little bit more and more and more. And after that, and at one point, because of that force created by that voltage is sufficient to break this depletion layer and this barrier, then as a result, the current is going through it. Then if we draw this one graph like that, we have, shall we draw like this? And this is the voltage we are applying across the junction. And this is the current we can see external path. This is a 0. And you know that until certain point. And here we have increased, we have given certain voltage, small voltage, but there is no possibility to go through the carriers to the other side. Because of that, no external path current. And it goes like this until a certain voltage. And after having this certain voltage applied here, this depletion layer will be broken. And then after that, the carriers can go to the other side. Then as a result, current is going like this. Okay. And this is the voltage, and we say this is forward bias voltage, VF. And this VF is 0.7 volts when we use silicon to make these semiconductors. When we use silicon, and you need 0.7 volt to break that potential barrier, and this VF is 0.3 volts if this material is germanium. Okay, you know that using silicon and germanium we can make both N-type and P-type semiconductors there, and we can make PN junction also there using the same using these two type of elements. And the silicon semiconductors and germanium semiconductors are having very much close characteristics, but some type of voltage levels and some kind of values may be different. And this is the one thing here. The silicon diodes, so silicon junctions, for the silicon junctions, we need 0.7 volts to break that potential barrier, and we need 0.3 volts to make that potential barrier if the material is germanium. Is it okay? Okay, if it is okay, then shall we try to understand what will happen then if we reverse the voltage? So now we have applied battery like this, but shall we change the polarity? And we take positive side to this side and negative side is here. And again, this is a variable one. Voltage can be varied. And because of this introduction, to the voltage to the other side, and this is the positive side of the battery, and this negative side. Then this positive charges are here and negative charges are here, and then Here the N-type semiconductors, majority carriers are electrons, and they are getting attracted to the terminal. Okay, the positive side semiconductor piece, the holes are the majority carriers. They are getting attracted to the terminal because the negative charges are here. As a result, what will happen? As a result, then carriers are moving away from the junction. Then as a result, this depletion layer will be widened. Okay, this depletion layer will be widened. Then width of the depletion layer also increased. Because of that, no conduction is possible here. Okay, the conduction is not possible here. Okay, now because of this, I think you can understand that when we increase this voltage and the depletion layer width may be increase more and more, then you can understand that the conduction is not possible. Then the frictional path, this current is zero. No conduction is possible. And when we apply the battery like this, and we say this is reverse bias of junction. Okay. In this case, you can see we apply positive to positive terminal and negative to negative terminal, then the current is going through the junction, and we say this is forward bias mode. And but when we apply the current in the other voltage in the other direction, we say this is a reverse bias mode. The reverse bias mode, you can see that there is no current going through. Now this is the situation, and we say this is reverse bias mode, and this is reverse bias. When we reverse bias the diode, you can see there is no current going through the junction. Okay. When we forward bias the junction, and we can see the forward current is there, and when we reverse bias the diode, there is no reverse current, but actually there is a leakage current. But we don't discuss about those things in your scope. And for the moment, you can assume the current is almost zero. And we have the very tiny current, very tiny reverse current there in nanoampere range. In the picoampere range, it's a negligible one. And for the moment, we don't care about that. Okay, hereafter, you can see the current is going through this junction. You can see that when we have PN junction like this, when you have PN junction like this is P-type semiconductor, and this is P-type semiconductor piece, and this is N-type. And we have these two terminals, and you know that when we forward bias this junction, current is going through this direction. Because of that, we we have symbol. Sorry, we have symbol for this one. This arrow indicates that the direction of the current is going through this one. This is the terminal, but again here we have a barrier. Okay. And this is the symbol to show this PN junction. And this is the structure, and this is the symbol for PN junction, and this is P side, and this is N side, and we don't say this is P side or N side. This is anode terminal, and this is cathode terminal. Okay, then, and we using this symbol hereafter, we don't draw this structure again and again. But if you want to describe this one, then only we draw this one. Otherwise, hereafter we use only this symbol. This is PN junction symbol, and we say this is not PN junction. Hereafter we say this is diode. This is the diode symbol, and you know the story behind this one. Okay, any question? Anything before we discuss diode application? Now we know about diode, and we know about this diode behavior when we apply voltages in both directions, and then we can discuss about diode applications. Okay, sorry that before we discuss about diode applications, and we can draw the characteristic curve of this diode for both directions of the voltages. The previous case we draw, and this is the voltage when we apply voltage in forward direction, and we saw that here there is no current going through that. After that, the current is going like this. But when we apply the voltage in reverse direction, there is no current going through this one. But after applying more negative voltages, this diode will be damaged. Okay, this is V forward, and here this is active region of this one. This is active region of the diode, and it's behaving like that. Is normally we can use that device safely here. But when we apply this voltage reverse this one, and this is This is V cut-in voltage. Beyond that voltage, if you apply more reverse voltage beyond that one, the device will be damaged. Device will be damaged beyond this point. And this is forward voltage. This is cut-in voltage. Beyond this cut-in voltage, the diode will not come back to its normal stage. It will be damaged. Okay, you know that here this VF is 0.7 volts for silicon and 0.3 volts for germanium. I'll show you data sheet of a diode. Wait a moment, I'll find that one. This practical diodes. You can see these values there. Wait, I'll find that one. Okay, I'll show my screen, then you share. You can see this one. This is diode data sheet. It's common for IN 4001, 4002 up to 4007. And you can see the low forward voltage drop and you can see this table. Okay. What is this IF? IF means forward current. Forward current is maximum 1 ampere. Through this diode, okay, through this diode, we can send maximum 1 ampere current. Okay. Then this is VRRM. What does it mean? See, you can see that the below table, VRRM. For IN 4001 diode, it's 50 volts. IN 4007, it's 1000. This is the reverse voltage you can apply maximum. If you apply this reverse voltage more than 50 volts to this IN 4001 diode, the diode will be damaged. Okay. Then, and this is the normal way of that showing this diode. Normal forward current is 1 ampere, and this voltage, the reverse voltage VRRM, they have mentioned like this. And this is in this data sheet, and many more information is there, but we are not going to discuss all these things. And this is the diode symbol and the physical appearance here, and the physical dimensions are also there. Okay, we can go back to the this one. And here when we have a diode data sheet, and normally in general they are giving two values. Okay, then for this IN 4001 diode, the general data sheet, it provides 1 ampere, 50 volts. This is the device number. All over the world, this is a standard. IN 4001 this is the one. And with this diode, they are providing two values quickly. For the quick references, they are providing these two values only. What does it mean? This is, what is this? This is forward current. Forward current, IF. And what is this? This is maximum reverse voltage. Okay, VR. VR, VCO, whatever the thing that in the data sheet they mentioned VRRM. Okay, this VR. And these are the two figures they are providing. Now we have some kind of idea about this diode. Okay, they ask a question, what is the name of this plot? This is diode VI characteristic curve, or simply diode VI curve. This is okay. Okay, now if you don't have any question further, then shall we move into the diode application? Okay, how can we use this diode? The first application is diode. We can use diode as a switch. How? So, switch means that through a switch, that when the switch is open, no current is going through that one. If the switch is closed, current can go through the device. Okay. Same thing we can apply here. For example, here you can consider we have a bulb and we have a battery. And we are putting a diode like this. Now what will happen? This here, this positive side is connected to the positive side of the diode. Then the diode will be forward biased, and as a result, the positive current, this one, the forward current will be going through the diode. Then this bulb is on. You can see bulb is working, bulb it's been turned on. Okay. Then what happened? Then this I, here I is greater than 0. I has certain value. Okay. We can calculate that one if you know the values. But in this case, this bulb is on. But shall we put this diode in the other direction? And then this positive terminal has been connected to the negative terminal of the diode. Then what will happen? As a result, no current is going through this one, then current is 0. Current is not possible. Because of that, the bulb is not turned on, then bulb is off. Okay, if you apply this diode like this, then here in this case, this diode is forward biased, this diode is forward biased, but in this case, this diode is reverse biased. Then through a reverse biased diode, there is no current, and through a forward biased diode, current can go. Okay, one other thing we can find out here. Assume that you have applied here this battery voltage is, assume that this battery voltage is 6 volts. Okay. Then across this diode, to break that potential barrier, to remove that depletion layer, how much of voltage do we need? If it is silicon diodes, we have to apply 0.7 volts to break that potential barrier. Then after that, across the diode, we have dropped 0.7 volts. Okay. Then how much of voltage the bulb has received? Here that's from 6 volts, we have to deduct 0.7 volts. Then across the bulb, it receives 5.3 volts. Okay. That voltage drop is there. Okay. You have to understand this one and you have to apply this one when you do a problem, when you do a design, when you do a calculation also. You have to apply this one, voltage drop. And especially at your examination, if you are asked to do that, if it is necessary to do that one, then you have to apply this 0.7 volts. In some cases, we don't care about this 0.7 volts. And without considering this 0.7 volts, you can do the calculation and you can do the drawings. Otherwise, if you are asked to consider this voltage drop, then specifically that you have to consider that one also. Okay. Then shall we have some questions before we move into next section? Okay. Then can we try to answer these questions? Then first we have this diode and this one. We can find out whether the bulb is turned on or not. We can say this is V1 and V2. And the second problem, we have two bulbs that, assuming that this is 3-volt bulb and this is 5 volts battery. Okay. This is B1, B2, this B1 and B2. Then find out that bulb on or off or then what are the things that what can we say about these things? So Didula, that what you are referring that the arrow be from higher to lower voltage and which diagram you are referring this one?
Yes, sir.
Here that the arrow should be here, that the voltage should be in this direction. The arrow head shows that the positive voltage level, and the voltage is in this direction. And here from this is positive negative. This is positive negative. These 6 volts will be dropped across the devices like this. This 0.7 plus 5.3. It's 6 volts from this side. The battery side, it's the battery side, the arrow is this direction. The other way, arrow should be in this direction. Is it okay?
Okay, sir.
Okay. In the first one, we have applied this battery in this direction. Because of that, the diode is reverse biased. Because of that, bulb is off. Why? There is no current going through the circuit. Okay, here, this 5 volts, this one. Across this diode, we have 0.7 volt drop. Across this diode, we have 0.7 volts, altogether 1.4. Then across the bulb, 1.4 been gone. Then across this one, we have how much? 3.6 volts. Then we can turn on the bulb is on, and forward current is also there. Here, this is the bulb direction, and because of that, this diode is forward biased and this is reverse biased. Because of that, this bulb is turned on and this one is turned off. Okay, here this diode is in this direction, positive to positive, and this diode is forward biased. We can see that this is forward biased, and this positive voltage can come to this side. And here you can see the positive voltage is coming to the cathode terminal of the diode. And the other direction also, you can come from this side also. And from this side, this is negative terminal, and it has been connected to the anode of the diode. Because of that, this is reverse biased. Then this is reverse biased diode. Then there is no current going through this one. Because of that, this bulb is switched off. Is it okay? Sarika, which one you are referring that? Is there any possibility to the little high voltage connected? Which one? 1, 2, 3, 4. Second one. Yes. Because that actually at the moment that bulb is expected to have the 3 volts, that is the working voltage, but here we have applied 3.6 volt. Because of that, they start asking that if you increase more voltage here, the bulb will be damaged. Yes. At the moment is 3 volts, 3.6 volts. At the moment is slightly, it's okay. But bulb will not be damaged because of the slight increase. But if we go beyond this one, if we increase more voltage, maybe 3 volt to 5 volts like that, then bulb will be damaged. Okay, if you are okay with this one, then shall we look at this way? Then we have this diode applied here, and here we have a resistor, and assume circuit like this. Then this is 6 volts battery, and across this one, you can see the diode is forward biased, then current is there, and across the diode we have 0.7 volts drop, and this across the resistor we have 5.3 volts. Okay, and this is the forward voltage across the diode, and this is the resistor voltage VR. If we draw this one on a graph like this, and this is voltage, sorry, this is time, and this is voltage 0, and this is the battery voltage VB, and battery voltage we applied is 6 volts, but VR we applied is and this is the battery voltage. Throughout the time we have applied 6 volt constant voltage. But when you measure the voltage and when you see the voltage across the resistor, it's less than that. Then this is VR. VR is 0.7 volts less. Here, 0.7 volts gap is there. Okay, because of the diode. Okay, assume that we have a circuit like this, and here we have this diode and this resistor here. And we have this V in voltage, resistor, diode. And can you find out the voltage? If our voltage V in is V in is, sorry, if we apply this V in voltage like this, what will be the output waveform across the diode, across the resistor? Can you draw the resistor VR? Assume that this V in here, this is plus 5 volts V in. And what about VR? At the same time, draw this one also. This is volt. Assume that your V in like that. This is V in. Draw VR.
Excuse me, sir.
Yes.
Can you show this circuit again for me?
This one. We apply this V in voltage here.
Okay, sir. Thank you. Okay, sir. Thank you.
Okay, then you can draw the output waveforms for this one. What about this one? Here the V in is 5 volts. It's changing in between 0 volts and 5 volts. 0 volts and here the 5 volts. And when the V in is 5 volts, VR will be how much? It's 0.7 volts less this one. This will be 4.3 volts. And it can change this one. And at 0, it's also 0. And it goes like this. And again, at here, it's 0.7 volts less than input voltage. Okay. What about this one? Here in this region, diode is forward biased, but here the voltage is applied in reverse direction, and during this region, diode is reverse biased. This case is forward biased. This is reverse biased. If the diode is reverse biased, there is no current or voltage going across this one. Okay, then we can draw the output graph. It's less than somewhat V in, and it can follow the sun, and it goes like this. What about this? It's going slightly below the input voltage. And after that, during this region, it's reverse biased. Then 0. And it's 0. Any question, anything? Okay, if you are okay with that, we can finish the class. I think I have had a discussion with your coordinator Chamat, and Chamat, are you there?
Yes, sir.
Okay, Chamat, that as we discussed that we plan to have a class in the evening today.
Yes, sir. From 3:15.
Yeah, I think it's still not be possible, Chamat, but anyway that we can have that tomorrow morning class, 8 to 10. Is it okay?
Yes, sir. Is it okay?
Okay, then in the meantime that I'll send that the possible time slot for me. Then we can discuss your batchmates, and after that we can finalize the slots.
Sir, as I discussed with Chandana, sir,
Yeah.
next week also possible for lectures.
That means the next weekend.
Yes, sir.
During the weekend, that is there any free slots, or the whole day is free?
The timetable is finished. Official timetable is finished from this week.
Okay.
So next week, I think at the moment we have no lectures.
Okay, then shall we fix that the Saturday 10 to 12?
Next Saturday. Sure, sir.
10 to 12. Then, but on Sunday that you have something, no?
No, sir.
You don't have anything. Then Sunday, I can do maybe 2 to 5.
2 to 5.
Yeah, then 2 to no, it's 2 to
2 to 5
4 we
means
can
3 hours, sir.
yeah, 2 to
Yes.
4 we can, if you are okay that we can have 4 hours. What do you think?
Sir, we'll give you a break and
Yeah,
then
we can have break, but whatever the way that we can have break, but not continuously. We can have the 15 minutes break, or in between 1 hour after that we can have the small break. Then we can start next hour. We can
It's
do like
fine.
that.
It's fine, sir.
Okay, then 2 to 6 we can do that. Huh? We can say 2 to 6, but in between that we can have the breaks, and then time maybe 6:30 we can finish. Then tomorrow we have Sunday we have 8 to 10. The tomorrow evening that you can't. Hello, Chamat. Okay, then tomorrow evening you have freshers night. No? Then we can't do anything tomorrow evening. Okay, then we can do only that tomorrow morning lecture. Then we can have that other one. The next weekend, Saturday 10 to 12 in the morning. I'll let you know that if it is possible to have week in the evening. But for the moment, we stick to our plan to Sunday, then 5th Sunday, 2 to 6. But you will have in between breaks, okay? Okay, I think Chamat has been disconnected, maybe.
Yes, sir.
Yeah.
I got disconnected, sir.
Okay, Chamat, then as we planned that tomorrow morning we have 8 to 10, and Saturday 10 to 12, and Sunday 2 to 6. Then we have 1, 2, 3, 4 classes, including this one 5. We need another 5. Right, we need another 4. As we discuss, you can have a discussion with your batchmates that the possibility to have night classes in the night, maybe after. Yeah, maybe after 8 to 10 like that, or maybe 7 to 9 like that. If it is possible, let me know. Otherwise, I'll upload some videos.
Okay, sir.
Okay. can have some small chat with your batchmates and let me know. Okay.
Okay, sir. I will let you know.
Thank you, Chamath, and thank you all of you for your support and your patience to these classes. Okay, thank you very much. We'll meet you tomorrow morning.
Thank you, sir.
Okay, until then, you can have a good day. Thank you very much.